You've used one thousands of times. You've never thought about what happens if the cable breaks. Here's the answer. To understand the scale, think about a high-speed elevator in a modern skyscraper like the Shanghai Tower. It travels at over 20 meters per second. That's fast enough to cover the height of a 6-story building every single second. The elevator car alone weighs several tons, carries up to 20 passengers, and must stop precisely level with each floor, every single time, thousands of times per day, for decades. By common sense, stopping that much mass at that speed, with that kind of accuracy, should require an enormous, complicated machine. But physics says otherwise. And everything you see in a modern elevator is the result of over 150 years of engineering, failed designs, and one invention that changed cities forever. The origins go back further than most people expect. Hoisting platforms existed in ancient Rome. Simple rope and pulley systems were used in European castles and factories for centuries. But they all shared one catastrophic flaw. If the rope broke, the platform fell. That made them useful for freight, but completely impractical for people. Nobody was willing to stand on a platform held up by a single rope. In 1852, an American mechanic named Elisha Otis was working in a factory in Yonkers, New York, and needed a safer way to lift heavy equipment between floors. He solved the problem not by making a stronger rope, but by designing a system that didn't need the rope to survive. He fitted a spring-loaded safety brake to the sides of the elevator car. If the cable went slack, the spring mechanism engaged automatically, driving metal clamps into the guide rails on both sides of the shaft and stopping the car instantly. In 1854, Otis stood on an open platform high above a crowd at the New York World's Fair and had an assistant cut the cable. The platform dropped a few inches and stopped. The crowd was stunned. Otis had not invented the elevator. He had invented the reason to trust one. After that, progress accelerated. Steam power gave way to electric motors. Open platforms gave way to enclosed cars. Manual operators gave way to automated control systems. In 1925, the first fully automatic elevator was introduced. No operator, no handle, just buttons. And somewhere along the way, engineers stopped designing machines that simply lifted boxes and started building systems that could move hundreds of people per hour through a skyscraper with the precision of a Swiss watch. But despite all the innovation, the core principle never changed. An elevator is always about one thing: moving weight up and down as efficiently and safely as possible. So how does a machine suspended by cables in a vertical shaft actually work? The answer lies in two fundamental principles that every traction elevator ever built depends on. The first is the counterweight. Every traction elevator has one. It is a heavy block of steel or concrete that travels in the opposite direction to the car. When the car goes up, the counterweight goes down. When the car descends, the counterweight rises. The counterweight is calculated to match the weight of the empty car plus approximately 40 to 50% of its maximum passenger load. This means that whether the elevator is going up or coming down, the motor never has to lift the full weight of the car and its contents. It only ever has to move the difference. That single design decision reduces the energy required to run an elevator by nearly half. Without a counterweight, every upward journey would require the motor to lift the entire mass of the car and everyone inside it from a standing start. In a building where an elevator makes hundreds of trips per day, that difference in energy consumption compounds into something enormous. The second is the drive sheave. This is a grooved pulley at the top of the elevator shaft, turned by an electric motor. The steel cables that support the car are looped over the sheave and attached to the counterweight on the other side. When the motor turns the sheave, the grooves grip the cables through friction, and the car moves. Up or down, depending on the direction of rotation. The motor doesn't pull the car up like a crane. It turns a wheel. The cables do the rest. In modern high-rise buildings, These cables are sometimes replaced with flat steel belts, reinforced with carbon fibers. They are lighter, quieter, and more flexible than traditional round cables, which reduces energy consumption significantly in buildings where the elevator travels hundreds of meters per trip. But here's what most people don't think about. The cables and the counterweight are only half the system. The other half is stopping, and this is where a common misconception needs to be cleared up right away. Elevators do not rely on the motor to stop the car. If the power fails, if the motor stalls, if the cable snaps, the car must still stop safely. That is non-negotiable. So every traction elevator has an entirely independent braking system that operates whether the motor is running or not. The electromagnetic brake is the first layer. It is mounted directly on the motor shaft and held open by electrical current. As long as power flows, the brake stays disengaged and the motor can turn freely. The moment power is interrupted, for any reason, the brake closes automatically under spring pressure. This is called a fail-safe design. The safe state requires no power and no action. It is the default, not the exception. The speed governor is the second layer. It is a flywheel connected to the car by a separate cable that spins as the elevator moves. The faster the car travels, the faster the flywheel spins. If the car exceeds its rated speed by a set margin, centrifugal force throws the flywheel arms outward, triggering a mechanical latch that grabs the governor cable. That cable is connected directly to the safety brakes on the car itself. The brakes are wedge-shaped clamps that sit against the guide rails on both sides of the shaft. The moment the governor cable is locked, the moving car drives those wedges harder into the rails. The faster the car is moving, the more forcefully the wedges engage. The braking force is self-amplifying. It increases with speed. The car cannot outrun its own safety system. This is exactly what Elisha Otis demonstrated in 1854. The mechanism has been refined over 170 years. The physics have not changed at all. Modern elevators add another layer entirely. The control system monitors the position of the car in the shaft to within millimeters, using encoders on the motor shaft. It reads the car's speed dozens of times per second. It calculates the exact deceleration curve required to bring the car level with the destination floor, and adjusts motor power continuously throughout the journey. The result is that the car doesn't arrive at a floor and then brake hard. It begins decelerating long before it arrives, following a precise curve that brings it to a smooth stop exactly at floor level. Every time, not approximately, exactly. That smoothness is not a comfort feature. It is the output of a real-time calculation performed on every single trip. And here is something most passengers never consider. The number of cables supporting the car is not a redundancy measure. It is an engineered safety margin. A modern traction elevator typically runs on between 4 and 8 steel cables simultaneously. Each individual cable is rated to support the full weight of the loaded car on its own. If one cable fails, the remaining cables hold. If all cables somehow fail simultaneously, the speed governor and safety brakes engage. If those fail, a buffer at the bottom of the shaft absorbs the impact. There are 4 independent layers standing between a cable failure and an injury. Not 1, 4. There is one final detail that most people never consider. The door system is not a separate feature. It is part of the safety architecture. Every elevator door has interlocks on both the car and the shaft. The car cannot move unless both sets of interlocks confirm that both doors are fully closed and locked. Not almost closed, fully closed. A gap of a few millimeters is enough to prevent departure, and the shaft doors cannot be opened from the corridor side unless the car is physically present at that floor. Without the car there, the interlock holds the door shut. This prevents the most catastrophic possible elevator accident, stepping into an empty shaft, from being physically possible under normal operation. Every time you step into an elevator and feel it rise smoothly to your floor, it seems unremarkable. But it is not. It is a counterweight precisely calculated to your building's load. A drive sheave gripping steel cables under controlled tension, an electromagnetic brake held open by current and ready to close in milliseconds. A speed governor ready to respond if the car moves too fast. A control system managing deceleration to the nearest millimeter. And a door interlock system that has been preventing accidents quietly for over a century. To me, that is what makes the elevator extraordinary. Not what it does. The fact that it does it thousands of times a day without anyone ever noticing